So far in the course, we have discussed two major topics. One is the relativistic wave equations, in particular Dirac equation and its solutions for simple potentials, and the second topic was the analysis of Lorentz group, which provides important constraints on the type of consequences of a theory, even when you do not know all the details of the dynamics. And now, these two pieces can be put together to construct a framework in which we can deal with problems of electrons interacting with electromagnetic field in arbitrary instances, and this framework is known as the theory of quantum electrodynamics. It can be formulated in many different ways, but I am going to follow the historical route, where knowing the ingredients, namely Dirac equation, Maxwell's equations and Lorentz symmetry, the features were combined into a perturbation theory structure, and that allowed calculations and predictions of the theory in many instances where the interaction strength was sufficiently small. This framework nowadays has been extended to a more powerful framework, which is formulated in terms of Lagrangians and path integrals, and from which even non-perturbative predictions of any theory can be derived, but I will not go into those details in this particular course. I will stick to the perturbative formulation, and that formulation can be obtained rather easily from the ingredients which we have already constructed, and that analysis requires a fundamental quantity which is known as the propagator. So, the next topic which I want to discuss is the so called propagator theory, which is essentially the description of how a wave functions evolves in presence of various sources in the background, and if one can do that, then one can include more and more complicated features of the theory in a perturbative framework to get higher and higher order accuracy in the solution. One thing which I will use is a framework which simplifies the notation, and that amounts to choosing the units where Planck's constant and speed of light are set to unity. So, what does this propagator theory amount to? It is essentially a solution for the wave equation in presence of a source, and there is a general framework available for so called linear partial differential equations, that the equations in presence of a source can be solved in terms of what are known as Green's functions, or more specifically 2-point Green's function, and this object is what we will call the propagator, and it is a rather straightforward scheme where you have say some linear operator acting on some function u, which produces the source v on the right hand side. For any generic v, the solution is obtained by defining the Green's function. Let me put the indices explicitly. It is the same operator, but now acting on an object which has two arguments, x prime and x, and the result is now not the arbitrary source, but a specific source, rather the delta function or a point object. The reason for doing this is that because the operator is linear, we have the general principle of superposition available. So, you can calculate the result for any arbitrary source by just clever superpositions of many delta function sources located at different points, and so the general solution now can be written as u at x is equal to integral g, or rather this should be x prime g x prime x v x integrated over dx. The reason it works now is quite obvious to see if you act on the left side by L of x prime. So, you have L u on the right hand side, L of x prime on the Green's function produces a delta function. The integral of delta function with v will just produce v of x prime, and that is the original equation. So, all that has gone in this is basically the superposition principle, which is a simple property of any linear partial differential equation. And in general, the problems which we are going to deal with are all problems of wave mechanics. They will all have linear partial differential equation, and they will obey the property of superposition. So, we just have to cast our problem in this generic framework, and the Green's function is extremely useful because it is a solution of the equation not in presence of any arbitrary force, but the solution in presence of a point source, and the point source solutions are generally very easy to obtain. One other feature which is all pervasive in our analysis is in problems with translational invariance. The Green's function cannot depend on two arguments independently, but it depends only on the difference. This is a consequence of a translational symmetry, and it is extremely useful in simplifying the detailed calculation. You do not need to have an absolute frame of coordinates, only the relative coordinates matter. Okay. There are other features which are also useful, and one of them is the so called perturbative framework, in which the interactions are treated as source terms, which means the linear operator which occurs in the equation is the so called Hamiltonian without any interaction. It will become the free particle Hamiltonian, and all the interactions will be moved in this equation onto the right hand side and treated by this perturbative framework. It becomes very convenient to expand the solution the power series in the interaction terms. So, it means that the leading order contribution will be no interaction at all, then the next correction will be one interaction, the next correction will be two interaction, and so on and so forth. And if the interaction is sufficiently small, this constructs a series which makes reasonable sense in terms of predicting quantities which can be compared with experimental result to better and better accuracy. This is a generic framework which we are going to use. I also want to say that the formulation here is written in terms of the space time coordinates, and for that reason it is convenient to construct these solutions in terms of boundary conditions which are specified at infinity in the position and the time coordinates. Then one can ask what happens in the detailed solution where the interactions are localized in a certain region. This framework is what is known as a scattering analysis, which means that interactions are localized in space and asymptotic states, in particularly t going to plus or minus infinity are defined in coordinate space, and since these are the states which are far away from the interactions, they will be the solutions of the free part of the Hamiltonian, and in this particular case of wave equations, these states are often selected to be the plane wave states. So, this also is an important part of the framework. In the perturbative analysis, we typically calculate processes which can be expressed in the scattering scenario. One more comment I would like at the general principles, which is that though the problem is formulated in space time coordinates, the calculations are easier to carry out in momentum space. The reason being that this allows us to use the full powers of the Poincare group, in the sense that we know the eigenstates of Poincare group are specified by momentum and the spin, and so we can explicitly label what happens to each particular eigenstate in this framework. It is also useful that the plane wave are also Poincare group eigenstates in absence of any interactions in the problems which we handle, and then the calculations become straightforward, and of course, one can go from the momentum space to position space and back whenever required by simple Fourier transforms, but it is just that one framework is more convenient than the other in case of calculations. Now, let us look at the setting up of the whole problem in case of quantum mechanics, particularly the non-relativistic quantum mechanics, but using the language of these propagators or 2-point Green functions. The problem here is written in terms of the Green's function language, which I can now express as the wave function at some time t prime and position x prime is an integral of the Green function times the source, which was the initial wave function. So, the Green function contains all the changes which can occur in the wave function due to whatever interactions there may be, and this is a evolution which is arranged to go from past to the future, also called the principle of causality. This is just analogous to the solution I wrote down for a generic linear equation on the previous slide, and these factors of I and integrals over position etcetera, they are all taken according to some convention. Many times this a kind of expression is referred to as Huygens principle for wave propagation, and it is correct to apply it in this particular form, because the evolution equation which we will deal with are first order in time. So, given a description at a past time, you can go to the next step in the future time. Oops, I made a mistake, there is a greater than sign in this causality, not equal to sign. Okay, so, this is a solution which we want. We have a corresponding equation which now can be rewritten in terms of the Hamiltonian and interaction. The original equation is I del by del t minus h acting on psi x t is equal to 0. We are going to rewrite this form by separating the free and the interacting parts. And the purpose of the formalism is, given that we can easily obtain the solutions of H 0, which are typically the plane wave states, how to obtain the solutions for some arbitrary potential V, and that is what the Green's functions allow us to do conveniently. On top of that, we have the boundary conditions, the asymptotic initial state is the plane wave. You can give it some label phi I at x and t, with t going to minus infinity, and we want psi at x prime t prime as the final state for t prime going to plus infinity. It is useful in this particular framework that the time ordering is here Galilean invariant. So, if you ensure that t prime is greater than t in one particular frame, it will always be true in any arbitrary frame, and so the causality is little easier to deal with. You have to find a particular frame where it holds, and then you do not have to worry about it in any other frame. This essentially is the setup of the problem. Now, we need to solve this machinery. So far it is only a formal machinery, but now we want to convert this expression to what will happen to the Green's function. So, g of x prime t prime here is the Green's function of the complete problem. We will not be able to solve it in full generalities, we will actually solve it perturbatively x prime t prime x and t is obtained perturbatively in terms of the solution in absence of any interaction which I will denote as G 0. It is a solution for the problem where the potential part V is 0 and H 0 is the only evolution part in the dynamics. So, this essentially will describe how a plane wave evolves. And so, G will then be expressed as a power series in terms of G 0. As usual with solutions of linear inhomogeneous equation, the generic solution is a arbitrary solution of the homogeneous part plus a particular solution corresponding to inhomogeneous part. So, arbitrary Green's function G will be G 0 as a solution of the homogeneous part plus all the effects which come as a particular solution involving the interaction V. One can now easily see that the equation has a simple form. The source term now is V times psi on the right hand side, and so the equation for G will look the same except that there is a delta function instead of the whole V. Then one can go back and forth between the equation for psi and the equation for G. They look very similar. Generically, the solution can be rewritten as the formal structure is G with x prime and x. I will omit too many indices as long as the notation is unambiguous. Here it is written as 4 dimensions. The solution for the homogeneous part plus the inhomogeneous contribution. V times G is now the source and multiplied by this homogeneous equations Green's function G 0 will give this result. One can easily apply the operator on both sides to get back the original term, where the operator is just I d by dt minus h. This is a general solution. It does not solve anything in any detail, because the unknown part G is appearing on both the sides, and so the way it is used is actually iteratively where one gets G equal to G 0 plus integral. The first time one just takes the leading term here and substitutes in this expression. So, it is g 0 x prime x 1 v x 1 g 0 x 1 to x. Then the next order one takes this whole result which came out of this expansion and puts it back, that gives a next order term. And so on and so forth, and this is the way the actual calculations are done. The Green's function for the free particle is known, rather we will evaluate explicitly what it comes out to be. The interaction is also known, and the interaction is used in a power series expansion, assuming that it is localized as well as small, and so one has the final result accurate up to a certain order in the interaction strength V. And this framework also is conveniently described many times in terms of space time diagrams, where one has some initial point x, final point x prime, and the leading contribution is just g 0. Next order involves one interaction which here is at point x 1, and then on either side of it is again the free propagator. So, this is the first order correction. Then one can have more elaborate schemes. So on and so forth, and the structure is simple enough to remember that in calculation of this Green's function, there is basically an alternating sequence of a propagator followed by a interaction vertex, another propagator, another interaction vertex, till you go to the final point, and the calculation is done up to a finite number of steps in terms of this interaction vertex, and higher order accuracy will result if you include more such terms. This is now the strategy in case of non-relativistic quantum mechanics. One can do the whole analysis of scattering from a potential in this framework. The final result comes out again in terms of this power series or the formal expansion that we wanted psi x prime t prime. We sent in some initial wave, and phi I at x prime t prime is just the initial wave, provided nothing happened during the whole evolution. So, it is the solution of the homogeneous part of the equation. Then the effect of the interaction is now given by this propagator, which follows the interaction of the complete solution at the point x 1 t 1. This is a superposition principle connected with the definition of the Green's function. Above v times psi is the source, we apply a Green's function and then you get the inhomogeneous part of the solution, phi I is just the homogeneous part of the solution. Again this is a complete description, but since psi appears on both sides of the equation, you can't directly solve it. Iterative procedure gives the solution in the same way that you take this psi, put it back on the right hand side, which means that right hand side will have phi I, which is the initial state, instead of the exact solution psi, and one can do the calculation up to a certain order. This also can be expanded iteratively. The central aim in all this calculation is basically to obtain the G 0, the interaction V, and then being able to do all the space time integrals in a clever way. We will see that these integrals are conveniently done not in position space as I have written, but in momentum space. But let me give another definition which is also quite useful, and that is the so called scattering matrix element and they are defined as what happens to the initial state, then whatever comes out, what is this projection onto a particular final state. We have to take this limit that t prime goes to plus infinity, and it is a overlap of some specific final state, a basis one has to choose with whatever solution which came out from solving this equation. This one is often written with this index plus, it means this is a forward propagating wave. It is equivalent to the boundary conditions which we have used, saying that the wave goes from t to t prime only when t prime is larger than t. And now this can be formally rewritten in terms of the initial conditions which we have. We will stick in this various constraints of initial state and final states. And then appear the integrals. There are d cube x prime, d cube x, phi f star x prime. The complete Green's function from x prime to x, and then the initial state phi I. So, this is just rewriting this final wave function as a initial wave function multiplied by the complete Green's function. When the complete Green's function is broken up into the homogeneous and the perturbative part, this gets further simplified. Just take this above equation and substitute g in terms of g 0. The first term is just overlap between phi f and phi I, which produces a delta function by definition of the Green's function. That is a trivial part of the scattering matrix, just means that it is a contribution corresponding to nothing at all happening to the initial wave. In terms of matrix language, it is identity matrix. And then there is a interaction correction, which can be rewritten as the final state, but now we do not have g, we have to put g 0, and then the potential appears, then with the potential comes the wave function propagating forward in time. This is a formal expression for what is called the scattering matrix. Actually, in the conventions which I have used, there are some differences between the space and time integrals, but you can sort it out. It is not very complicated. This is a generic definition, and many results are expressed in terms of the non-identity part of this particular scattering matrix, which is this second complicated integral, and which one has to evaluate again by expanding psi plus iteratively. One has now iterating sequence of propagators and vertices, but on either side those are evaluated as expectation values between some initial state and some final state wave function, and that will produce this S matrix. What one finds is the Hermitian Hamiltonian will have a complete set of orthogonal eigenstates. This phi I and phi f are specific instances of them, and unitary S matrix. This is a standard feature of quantum theory, Hermitian Hamiltonian and unitary evolution. One has to remember that this completeness sum includes any bound states if they exist. In particular, the asymptotic states might be just plane waves, but in the intermediate steps, if there is any sum over complete set of states and if bound states exist, they must be made part of the calculation to get a valid result. So, this is all formal machinery, and now one has to implement it in case of specific Hamiltonians, and what we need to do little carefully is implement the constraint of causality. Once we have done that, we have the Green's function solution, and that is the place which requires little mathematical tricks to be able to do the calculations. Causality is included using the step function, which has the behavior that it is equal to 1 when the argument is positive, if it is 0 when it is negative. Related to this step function definition is a definition of the delta function of the same argument, which is the derivative of the step function is the delta function. We can now include this extra condition by just inserting in the differential equation a factor of the step function by hand, and then we do not have to write that particular condition separately. And so, the equation can also be written as psi at x prime is g x prime x integrated with original state psi of x, theta of t prime minus t. Explicitly make sure that if t prime is larger than t, you have a actual solution. If t prime is less than t, then this whole integral over Green's function vanishes. That is now convenient because the step function has many convenient integral representations, which are easily written in terms of Fourier transform variables using contour integration we find that this theta of tau can also be written as an integral from minus infinity to infinity d omega e raised to minus I omega tau divided by omega plus I epsilon. That is the crucial part of the prescription. So, the pole is at omega equal to minus I epsilon. This pole is slightly below the real axis, and that produces this step function behavior by closing the contour in different manners depending on whether tau is positive or negative. When tau is positive, then to make this exponential factor decay at infinity in the complex plane, one must close the contour in the lower half of the plane. So, this is the integral from minus infinity to infinity, and one closes in the lower half of the plane. The pole is included in the region of integration. Residue theorem gives the result, the 2 pi I coming from the residue theorem, including a negative sign because the contour is closed clockwise, exactly cancels out this factor in front, and all one is left with from the contribution of the simple pole is the result that it is 1. That is how when tau is positive, the answer is 1. If tau is negative, then the contour is closed in the upper half plane, because then the imaginary part of tau gives exponentially damped phase at infinity, and this semicircle can be added to the contour without any problem. The integral over that vanishes, but now the pole is outside, and so it does not contribute to the integral, and literally one obtains 0. This is a kind of clever trick to write the step function as a integral over an energy variable, but now adding a pole which is slightly away from the real axis. Shifting is by this amount epsilon, and epsilon is going to 0. So, that at the pole this factor e raised to I omega t basically becomes 1. This trick allows us to rewrite the result for the Green's function, which we are looking at in the non-relativistic problem. We have the equation for the Green's function and the unperturbed part of the Hamiltonian can be written in coordinate space as minus del square by 2 m The propagator is easily obtained in momentum space. The delta function Fourier transforms to just 1, and so the Green's function is nothing but the reciprocal of the operator which we have on the left hand side, except that now we have to write this particular operator in momentum space. That becomes one over omega from this del by del t p square by 2 m from h 0, and on top of that we add this I epsilon prescription to ensure that this Green's function is non-zero only if t prime is bigger than t. Now, using this particular propagator together with a potential, a calculation in non-relativistic quantum mechanics of any scattering analysis can be carried out. So, this is an illustration of the formalism and a simple result. We will build on it in the next lecture to look at the relativistic case.